Next, we take a look at parameters and families of functions. So a parameter is basically a variable-like quantity that is held fixed. So it's treated as a constant. So a parameter will look like a variable. In fact, on one level it is a variable, but it's held fixed. Right. So basically, when you're actually computing or analyzing a problem, you treat your parameters as fixed. You treat them for fixed as long as you get to a solution. Once you have a solution, you can plug in any values for those parameters that you wish. Now, why is this useful? Well, it's useful because sometimes you have a score of related problems. So for example, suppose you're analyzing airplane wings. So you have wings that have a bunch of different lengths. There might be some other physical parameters, like there might be a drag coefficient, which is called gamma. So let's say that each wing has a different drag coefficient and it has a different length. And you want to solve some problem about the wing. For example, how much lift are you generating with your given airplane wing? Well, if you have 30 or 40 different airplane wings and you want to find the answer for all of these, you'd have to solve the problem 30 or 40 different times. Instead, what you do is you can say assign a variable name for certain physical quantities, such as the drag coefficient and the airplane lift, and write your equations in terms of L and gamma. And you treat L and gamma as a constant because for any given wing, L and gamma are a constant. Right? And then you solve the problem. And when you solve the problem, whatever the problem is, you then have a formula that involves L and gamma. Now, when you encounter a real physical airplane wing, you can then just look at your formula and figure out the length of the wing and the drag coefficient, plug those into the formula, and you have the answer for that particular situation. You've seen this before. The volume of a sphere is 4/3 pi r cubed. So at one level, you can think of r as a parameter. You can also think of it as a variable. But if in the actual derivation of this, r is basically a parameter. It's held fixed when you would actually compute this. You will compute this volume in calculus 3, so we'll see how that's actually computed. And during the course of the calculation, we have to treat the radius of the sphere as a fixed constant. So r is there as a parameter, not as the variable. Another example is, suppose you have a skyscraper and you have a person who's throwing or dropping a rock from a particular height with different mass. So there's a mass and you have an initial height h, and you're releasing and you want to find out how long it takes to hit the ground. Well, instead of solving this problem over and over again for different masses and different heights, maybe the mass somehow factors into the air resistance or something. Probably not, but you would just solve it once using your parameters. So m might be a parameter, h might be a parameter, and so forth. And then you have a formula that would involve m and h. And then when you say, okay, the mass is this mass and the height is that height, you can just plug it into your general formula and get an answer. So parameters are also useful in describing families of functions. So the simplest one, we just have mx plus b. So here, m and b are parameters. And this formula gives us basically a two-parameter family of functions. So in other words, we have these two parameters, m and b, and for each value, you get a different function. So for a fixed b, you might get a function like that, like this, like that. So these are different values of m. And then for other values of b, you get more functions. So it's a whole family of functions that are related. They're all linear functions, and they're all related to each other. They have the same basic form, but you just have different numbers standing in for m and b. Another example would be y is equal to e to the ax. So here's e to the x like that. Now if we say e to the 2x, so we know that that's basically a horizontal compression, so that everything gets compressed in by a factor of 2, which means that on this end it decays more rapidly as x goes to minus infinity, and then on this end it grows quicker as x goes to infinity. If you have 3x, it's like that. So this might be e to the x, e to the 2x, e to the 3x. That's just e to the 0, so it's just a constant, it's equal to 1. And then you have maybe e to the minus 0.5x. Maybe that's e to the minus x, e to the minus 2x, and so forth. When you do the negative, so this is e to the minus 2x. E to the minus 2x will be a reflection of e to the 2x about the y-axis. And it decays as x goes to infinity instead of growing as x goes to infinity. So all of these are exponential functions. They all take the same basic form, but for different values of the parameter a, you get a different member of this family. So you have a bunch of functions that look together. So one can often combine different transformations of functions. So this is horizontal and vertical stretches and compressions, translations, and reflections to get families of functions. So you have families of functions that all behave similarly based on the parameter value that you obtain, or the parameter values that are present.